catch up technologically. We need a fresh approach that delivers results today. Fortunately, millions of years of natural evolution has produced a model of highly coordinated behavior within and across species that allows massive flocks, colonies, blooms, herds, etc. of individuals to form distributed collective intelligences whose whole is greater than its parts. Now, we are using this natural organic approach to harness the power of narrow AI to create truly smart city ecosystems. Now, in this session, we will dive into the details of the approach, its advantages, and its application in the real world. So this is a session that's going to be on the data-driven intelligence, organic ingredients, and doing this for us is Philip Desautel, member, NCG Advisory Board, CTO, Tondo IoT. Now, a little about him. Building on 25 years of industry experience managing technology, Philip builds on his wide-ranging experience inside and outside the technology industry to head product at Tondo. Now, he's on the NetConnect Global Advisory Board, and prior to this, Philip served as an executive director of IoT at the Linux Foundation, leading global open source projects in consumer and industrial IoT. He was also the CTO at LogMeIn, where he co-founded, built, and launched Zively, the world's first commercial IoT platform, recently sold to Google. Now, he was a co-founder of IoT Works and Internet of Things Research and Investment Group. Philip spent nearly 10 years at Microsoft running strategy and evangelism teams. He was also the chief scientist at MathLogic, or Excite at Home. So without further ado, I'm going to hand this over to the capable hands of Philip Desautel. Congratulations on everybody who's logged in for a wonderful session. Over to you, Philip Desautel. And Philip, may you please finish this on time, because you will hear a gong 3 minutes before your time is up. All the best to you.
Yes, thank you very, very much. And thanks for that great introduction. I am going to jump right into the session, and I really I want to thank everybody for all the sessions that preceded me. It was I got up early this morning to really absorb the content. I think this talk is going to fit well with it. So let's jump in. Let me introduce the humble honeybee. She lives 2 to 4 weeks and makes 12 trips a day from our hive, where she visits between 50 and 100 flowers on each trip. For all of her effort, she will produce 1 gram of honey in her lifetime. She works together in a colony of about 50,000 individuals that together fly the equivalent of the distance from the Earth to the moon every single day. For all of their combined efforts, these bees will produce about 45 kilograms of harvestable honey per year. When our little bee returns to the hive laden with pollen, she does a little waggle dance to tell her sisters what she has found. The type of pollen, its distance, its direction, and its abundance. We can think of this as bee telemetry. As each successive bee comes in, the hive gains more telemetry, more knowledge. At some point, the group of bees waiting to depart makes a collective informed decision based on the data they have gathered and their own historical knowledge. Now they go off on foraging missions of their own. When they return, they repeat the process. Each group collects data, processes the data, and makes a collective decision. This last part is really important, the collective decision. They don't have a vote. They don't hold a ballot. The bees are doing what science describes as synchronous actions of coordinated behavior in a closed-loop system. Or more simply, they are demonstrating collective intelligence. And we heard this in some of the other sessions before me. This is the first element of our organic model. Time and again, as we explore biological systems, we find that social creatures of all types that work together in collaborative systems outperform a majority of the individuals within those collectives. The hive, acting as a collective, is smarter than the individual bees within it. This is the second element of our organic model. And then finally, we see that these collaborative communities behave as coherent entities. That is, they act as one. This is the third element of our model. So let me jump from the bees to outdoor lighting. Meet the humble street light. There are approximately 350 million of them in the world. The traditional incandescent version is rapidly being replaced by LED lights. LED lights are 40 to 60% more efficient. In the United States alone, replacing outdoor lighting with LED lighting would save $6 billion annually and would reduce carbon emissions by the equivalent of 8.5 million cars. In India, street lighting, electricity, and maintenance costs can consume 5 to 10% of municipal budgets in large cities and up to 20% in smaller cities. The switch to LED lighting just makes sense. The switch to LED lighting also presents a huge opportunity in terms of capability. If we take that LED fixture and we add a smart lighting controller to it, we now have a light fixture that is individually controllable, on, off, dim, programmable with schedules, and capable of semi-autonomous actions tied to outside inputs. For example, brightening a path when somebody walks by. A smart lighting controller can increase energy savings by upwards of 75%. But this is just the start of the advantage that smart lighting brings. A smart lighting controller can host a variety of sensors, enabling it to collect a wide array of data factors, including power consumed by the fixture, detailed information on the grid itself, and environmental parameters, just to name a few. And because our lighting controller is connected, it can report all of this telemetry data, collected and computed, back to the cloud. Our smart lighting controller is starting to look a lot like our little bee. The telemetry from our smart lighting controller lands in the cloud. Here, powerful AI tools process incoming and historical data using analytics and machine learning techniques to monitor the health of the light fixture and its environment. How much power was consumed by the fixture? And is this what was expected? Is the light engine operating as expected, or have some of the LEDs failed on it? Is the power grid okay? Exceptions from the norm can trigger immediate actions, say in the event of a failure, or they can indicate that preventative action is needed. Data collected and created in this process becomes the basis for additional analysis and reporting. When the AI processes data from each streetlight, it creates data exhaust. This exhaust, or analytical metadata, along with data streams and historical data, becomes the input for subsequent analysis. At this point, what I'll term second-order AIs are applied. These AIs are looking across fixtures, geographic outages caused by a circuit failure, long-term group reliability problems brought about by repeated power supply issues. Additional data exhaust at each tier becomes the input for the next tier, and so on and so on. We apply as many layers of analytics and AI as we need to answer the specific questions we have. This AI-driven model of smart lighting represents the state of the industry today. Light fixtures that are remotely managed, monitored, and controlled, centralized systems that process telemetry data to detect faults and identify opportunities for preventative maintenance, data pools that deliver detailed reporting and accounting, open AIs that allow bespoke integrations. This sounds a lot like the sessions we've heard today so far, and it is. So what, you might be saying? So far, this is all just normal workaday elements of modern industrial AI, smart connected devices collecting data and sending it to the cloud where analytics and AI are applied to make sense of it for business purposes. Where does the organic element come in? We want to see collective intelligence, something that wows us, not just your thinly veiled marketing. What this model lacks, and I heard this in a couple of the sessions just before I came on, it is autonomy. Everything I've described so far is prescriptive. It depends on me knowing what I want as an outcome. Let's go back to our bees, who seem to be able to overcome this challenge. Earlier, I described their collective hive intelligence. If we want to go from our individual actor, the smart street light, to a collective intelligence, the smart city, we need to make a leap from explicit narrow AI to an organic model that encompasses synchronous behavior, coordinated actions, and closed-loop systems. The first step in making the leap to organic collective intelligence is to add synchronicity to the architecture. We begin by giving controllers a way to intercommunicate. If we shift from our classic IoT star model where devices talk to the cloud and the cloud talks to devices, to a mesh where a constant chatter, a waggle you might say, among devices creates a rich level of information sharing betwixt and between controllers, we start along the path. But we're not there yet. Now we need to give our controllers context, a sense of who they need to synchronize with. This is a complex since the context of who is part of the group changes with the desired goal or goals that any given controller has. One way to do this is to imbue controllers with what I like to call O-graphics. This is from my advertising time. Geographic, where I sit physically. Gridographic, where I fit into the electrical circuit architecture. Wayographic, where I fit in the moving world. And useographic, what purpose I serve. These become part of the knowledge base of each controller. In this way, controllers to begin to know, if you will, where they fit in. If we empower controllers to share information into their conversational mesh, to waggle, and imbue them with simple AI that establishes rules for coordination across context, then we enable autonomous synchronous activity. The next step towards organic collective intelligence is to leverage synchronicity to deliver coordinated behavior. To do this, we need to give our controllers a purpose, a mission. Like our little bee foraging for pollen whose goal is to feed the hive, we want our controllers driven towards an end. Our controller's mission might be to be as efficient as possible, or to strive for the safest lighting in a park, or it might be a combination of multiple goals. The important element here is that our controller has a goal. With a clear goal and an established context, all that our controllers need in order to take coordinated action is shared information from their peers, which comes through the waggle and chatter, and from the world around them. For example, traffic and weather data. As each fixture evaluates its context and the streams of data flowing past it, it can start to decide which actions it wants to take to achieve its goal. But the magic of coordinated action is that they are taken collectively. The intended action of each member of the contextual group gets shared and evaluated by other members of the group until a decision point is reached. When this happens, the group has consensus and it can act as one in a global coordinated way. Now we get to the final and most challenging part of the organic collective intelligence model. When we say it's a closed loop system, what do we mean? Formally, a closed-loop system is a system that automatically regulates itself to a desired state without human interaction. In traditional smart street lighting systems, the system is open. Humans set the schedules, monitor for problems, make manual changes, and work to achieve their goals. Sure, the system has automation tools that make that work easier, but these do not automatically act beyond some very tight constraints. If we want to begin building organic collective intelligence, that is, systems that are self-regulating and self-optimizing, we need to find a closed-loop system that we can automate. Where do we draw the line for a closed-loop system? Manage the city lights is a staggering problem. Consider my hometown of Boston. It has 67,000 streetlights. Trying to make that entire system a closed loop on day one is an almost insurmountable challenge. I read a statistic that Delhi has 700,000 streetlights. Imagine trying to make that a single system right out off the bat. We need to constrain our scope. Our first attempt has to be something more like our little foraging bee convincing her sisters that she has found a great source of pollen, and less like a fully functioning hive. Biologists have modeled organic systems, and their research shows that by starting small and growing the model, we can continue to expand it to the point where the scale of our model equals the scale of our challenge. Implementing collective intelligence through synchronous behavior and coordinated action in a closed-loop system is going to take a substantial amount of work. But as we've heard from previous speakers, this general AI model is where we need to go. Components and subsystems have to be created, infrastructure needs to be plumbed, and communications need to be formalized. As we create systems and systems of systems and systems of systems of systems that embody collective intelligence, we move closer and closer to a shared vision of a truly smart city. And we get one step closer to holding in our hands the tools that we need to tackle the significant problems facing humanity today. We truly believe that just as moving from analytics to narrow AI was a game changer, moving from narrow ML-based AI to organic collective intelligence is an equally big, or maybe even bigger game changer. I've presented the model in terms of my business, smart street lighting, but the concepts are widely applicable to any business that has a large number of processes that can be orchestrated into a larger organic whole. Bringing such an audacious model to reality takes an incredible effort. Tondo's been very, very lucky to have NCG with its deep domain expertise as our partner. And as a result, we believe that we will fundamentally change the very nature of smart city enablement. The model I've outlined here is highly applicable to IoT, financial services, logistics, retail, and more. And I encourage you to consider the possibilities of a biological model on top of your AI tools. Finally, don't consider my opening in this talk a rebuke of AI and the introduction. The AI we have today is incredible. It does incredible things and it has amazing power. I just think that the challenges we face are so big that we need to do more. I heard my magic little ring, so I'll close with thanking you very much for your time at the end of a long day of amazing sessions. And I challenge you to think like a beekeeper. Don't get lost in the individual bees. Focus on the hive and then the ecosystem that it lives within. Thanks a lot. Riaz, back to you.
Thank you so much, Philip. What an organic thought, actually, with that lovely picture. The way you ended it is actually resonates a message in everybody's minds. All the best to you and in all your endeavors. We're going to wish you great luck. With that, yes, Philip, thank you so much. With that, ladies and gentlemen, please.